Chapter 8 and the 9.1 up to 9.3 is what you might need to know for the exam. Are there any other questions, exam related? Yes.
Will we have to memorize any sort of McLaren series stuff, like memorize what they all are and stuff like that?
Okay, you don't, technically you don't have to memorize anything, because you could, any McLaurin series or anything, because you could figure them out without too much work. But I would recommend knowing the basic one, 1 over 1 minus x, e to the x. And actually, if you start with those two, you can get to most of the others pretty quickly. So at least memorize those two, I would say. Yeah. I will not order the TA's email practice exam until they're all posted on the website, the Common Course website. You can always check there, and solutions will also be posted there.
So is it not on Husky CT?
Not on Husky CT, no. The Common Course website, where there's an outline for the course and like exam rooms and all of that. Other questions?
Yeah.
Yeah.
Is there a quiz this Thursday?
No.
Yeah. Oh, okay. All right, so again. You want to quiz this Thursday?
It's closed.
I heard someone ask, why would you want a quiz? My feeling is that if you guys take more, then I would be okay dropping more. Which is why you might want a quiz. You guys have never answered this quickly. It's on. And you will not have a quiz.
Yeah.
Okay. No quiz on Thursday. Your sections will just be review. The TAs will just review last minute questions and all that kind of stuff. Any other questions? Yes?
Are you going to hold a review session?
I still don't know if I will be able to hold a review session. So if you're interested in a review session, just watch your email and I'll send an announcement if I can't hold one.
Maybe we should vote. Let's vote.
Vote on.
Yeah.
I know, but it's not up to you guys. It's up to my schedule. There is a Q Center review session. Do you know when it is?
Yeah.
You can always go to the Q Center review. What was the room? This is Calc 2. This is Calc 2 specific Q Center review, which you can definitely go to. Do you have anything? Okay, and it's possible that the other Calc 2 professors will be having reviews, and I don't think they would have a problem if you guys wanted to go. But I don't know when they are. So you have to do a little detective work. Yes? What is the course website? Just go to math.ucon.edu and find it from there. Any others? Questions? Okay, so at the end of class last Friday, a few people came up and told me what their question was about all this binomial coefficient stuff. So I can at least answer their question, and hopefully that clears it up for more people. The idea is, their question is more of why do we care about these binomial coefficients? And so I'll put it this way. There are two easy-ish ways to derive the Taylor series here. One one, you could take 6 derivatives, or 2, you could use binomial coefficients. And so it's just 2 ways of coming up with the same thing, really. But there's never anything wrong with that. And the binomial coefficients here were these guys, the p choose k, p factorial, k factorial, p minus k factorial. And then the big idea, I guess after you finish writing. The big idea was that we modified this for fractional exponents. Or actually, any real number exponents. Which is why I did this example. Modify that formula, and now p choose k, we can just say it's p minus 1, p minus 2, all the way down to p minus k plus 1 over k factorial. And there are, again, these same two ways of figuring out the Taylor series. You could do derivatives and derivatives. This time you have to take derivatives forever. Or if you want to know what those coefficients are, they're based on this formula. So let's say the point of these binomial coefficients are so that we could write the Taylor series for this function. So, does that clear up any of the confusion? Should I put this to a vote? I will, just because it's the last time. Yes, I'm okay, I can move on as A. And D is no, I would love to hear you talk more about it. It's thrilling.
If you try a couple of examples, maybe it's gonna
A
help.
couple of examples? Well, okay. While you guys are voting, let's just say choosing 0 is always 1. So, you just, following the formula, we have p times p minus 1 over k factorial. 1/2 choose 3, 1/2 minus 1 of that, minus 1 of that, over 3 factorial. All right, these equal some numbers. What is that, negative 1/4, negative 1/8. This is 3/8. So, I did this last time, didn't I? And so the Taylor series is going to be 1 plus 1/2 x minus 1/16 x squared plus 3. What is 48 times 6? 288. And so on. So using binomial coefficients, we could find a Taylor series expansion for 1 plus x to 1/2. Yeah. What about? Okay, I don't want to spend too long on this, but this formula is equivalent to p factorial over k factorial, p minus k factorial, if p and k are positive integer if they're not, then this formula doesn't quite make sense because 1 half factorial, what is that? And so we modify it and we get this version, which works if p is a fraction. Or any real number. Yeah.
Let's go back just a little bit.
Okay, what did you guys think? Okay, great. Move on. Move on. So how would I write this in the sigma notation? I would write it exactly like this.
How would you
What?
how would you break P2K? Pick one.
How would I write p choose? P choose k is, that is how I would write it. Now I'm realizing I just messed up. I was going too far here. Sorry, the p choose k accounts for dividing by the factorials. If you found the derivatives and computed the Taylor series that way, that's when you need to divide by the factorials. Yes?
You said you were moving on, in fact, some people want you to talk more about it.
Yeah, you switched around. B was
Oh.
like stay, A was move on.
Stay. Oh, okay. Questions then? Yes. Yeah. Should we do that? Should we do some derivatives? Derivative of that, 1 half 1 plus x to the
Negative.
negative 1 half, right? And the derivative of that is negative 1/4 1 plus x to the negative 3 halves, right? And if we go then and plug in x equals 0, we get 1 half. We plug in x equals 0, we get negative 1/4. So our Taylor series coefficients are f of 1, f of 0, which I don't have up here, but f of 0 is 1. F prime of 0, which is 1 half. F double prime of 0 divided by 2, which is negative 1/8. And those are what we got here the other way, 1 half, negative 1/8. Yes.
Will we have a choice of like doing the binomial coefficients versus the derivatives on the exam?
Probably not.
Or will it specifically state?
Yeah, I would imagine so.
What if in this function equals 2x plus 1 to the 2x plus 1 squared? How would we use binomial method?
2x plus 1 squared?
Yeah.
Just not 1 over? Or
No, we did x plus 1 to the 1/2 power, right? What if it was that?
this?
Yep.
Well, this, I mean, then you could just multiply this out would be the easiest way. In general,
But what if we have to do it in the
Okay.
binomial way?
x plus y to the k is the sum of, I shouldn't use k, I'll use p, match my other notation. There's the sum of p choose k, x to the k, y to the p minus k, k equals 0, p. So I can cover anything, whatever x and y are. Are there more questions?
So say we have like x plus 1 to the third,
Yeah.
would it be 3 choose whatever?
Yeah, so x plus 1 to the third
inside derivative is 1? You know what I'm saying?
They can work otherwise. I'll do 2 examples in a row. Okay. Right, so this is going to be, this is the sum of 3, 2k, x to the k. We don't need the 1 to the p minus k part. K equals 0 up to 3. So that's 3 choose 0, plus 3 choose 1, x, plus 3 choose 2, x squared, plus 3 choose 3, x cubed. You plug in the formula for each one of these guys. 3 choose 0, and 3 choose 1, and so on, and you get 1 plus 3x plus 3x squared plus x cubed. I just have worked with these enough that I don't want to use a formula, but you guys can plug into the formula. And that's what you would get if you just multiplied out x plus 1 cubed times x plus 1, just did x plus 1 times x plus 1 times x plus 1, boiled all this stuff out, you would get this. And so think of binomial coefficients as your shortcut to that. And this shortcut is also useful if your exponent is not a whole number. Then the next question is, what if your derivative inside is something else? If you had something like this, it would be 3 choose k, 2x to the k times 3 to the 3 minus k. Choose 0 times, not times x, 3 choose 0, plus 3 choose 1, times 2x, cubed, plus choose 1, 2x, 3 squared, 3 choose 2, 2x squared times 3, plus 3 choose 3, 2x cubed. Yeah.
In the previous example, how did you get 1 plus 3x plus 3x squared plus x cubed? Where did you plug in the numbers to get 1, 3, 3?
Because 3 choose k, using this formula in each case.
Okay.
Right. So 3 choose 2. Need 3 factorial, or 2 factorial, and 3 minus 2 is 1, so times 1 factorial. 3 times 2 times 1 over 2 times 1 times 1, which equals 3. Other questions? I'll say I don't think you guys want to spend this much time on this. Like, it's a part of the thing that I'm teaching you, but it's not a huge major part. So, yeah.
Can you do absolute error approximation?
Oh, that's a great question. Oh, I have some other examples first, and then I'll
Yeah.
do something like that. All right, so I guess the idea here is that we're just doing some different ways of coming out with Taylor series. Right? You can almost always just do the derivatives out, and that's fine, but maybe your function doesn't allow that. So these examples are how you could generate a Taylor series for something you don't know from one that you do know. So like 1 over 1 plus x, maybe I've done this before, but you start with, okay, 1 over 1 minus x, that's one I know. You guys know this? How many do? Yeah, okay. You should. Right? It's all this, so it's the sum of x to the k. And so you can do some substitution. Say, well, 1 over 1 plus x is 1 over 1 minus negative x. So it's like this Taylor series, but with negative x instead of x. And so instead of the sum of x to the k, it's the sum of negative x to the k. And then we have the Taylor series for 1 over 1 plus x. So just using a substitution into a Taylor series we already knew. Or you can mess around like, let's say now we want 1 minus x over 1 plus x. Well, I could say that's 1 over 1 plus x, that's one I just figured out. Minus x over 1 plus x. And so we have 1 minus x plus x squared minus x cubed. Right, that's 1 over 1 plus x. And what would x over 1 plus x be? So how can you write x over 1 plus x using Taylor series you already know?
The same,
What?
the same thing as before, but times x.
Yeah, it's just the same. It's 1 over 1 plus x times x. So it's like it's x times 1 times x plus x squared minus x cubed. Right? Sometimes it can be helpful to write it out this way instead of summation notation. So it's minus all this stuff. Minus x. I don't want. Yeah, okay. Sorry, I'm just figuring out how to do my parentheses. Minus x squared plus x cubed minus x to the fourth. And if you simplify, you get 1 minus 2x plus 2x squared minus 2x cubed plus 2x to the fourth, and so on. So now we have a Taylor series for 1 minus x over 1 plus x. And can you guys write that for me in summation notation? Maybe not.
2x to the k.
Well, it's not 2x. I don't know. Never mind. Forget that question. Let's see. It could be negative 1 to the k. Oh, it's kind of messy, isn't it? All right. Well, x to the k equals 0, infinity, and then minus 1. Sure. This minus 1 is outside the sum. That part is not super important here. The idea is how to generate the Taylor series of something new from something you knew already. So, questions?
Why is it minus 1?
Because if I didn't have the minus 1 here, this would be a 2. Okay. Okay, let me see. Let's see how we're doing. So you can generate this new function from functions we know already. And then you can figure out the coefficient of the third degree term. So take a minute or two. Because obviously a lot of people are wrong. Whatever the answer is.
Is it B?
I don't actually know off the top of my head. I can figure it out though. Let's do it together, but I want to know where you got stuck. So I guess you guys tell me what you were able to do. What function is this related to? Related to 1 over 1 plus x? How are those related? What? The derivative. What's the derivative of tan inverse?
1 over x squared plus 1.
Okay, so these two are related. Tan inverse is the antiderivative of 1 over 1 plus x squared. Do we know the Taylor series from 1 over 1 plus x squared? We know 1 over 1 plus x. Could we get from one to the other? One over 1 plus x is negative 1 to the k, x to the k, right? So that means 1 over 1 plus x squared. Negative 1 to the k, x squared to the k. Or in other words, negative 1 to the k, x to the 2k. Pleasant. So I'll pause there for questions and let you get it right. Okay, so this is 1 over 1 plus x squared. 1 over 1 plus x squared and this big infinite sum are the same thing. That's what we're saying. Yeah.
Say there was a 2 in front of the x squared, but you just put that.
Then I would put a 2 inside the parentheses here. If it was 1 plus 2x squared, I'd say 2x squared inside the parentheses. So that means, well, tan inverse of x is the antiderivative of 1 over 1 plus x squared. And 1 over 1 plus x squared, we're saying is the same as this big infinite sum thing. So it's the antiderivative of negative 1 to the k, x to the 2k. And antiderivatives of polynomials, luckily, are pretty easy. Just using the power rule, we have a constant up front, negative 1 to the k, and then x to the 2k plus 1 divided by 2k plus 1. So maybe we should write it out now. So when k is 0, then it's x to the 1 over 1. When k is 1, then it's minus x cubed over 3. So there's our 3 term, coefficient is negative 1/3. Only people who jumped to D when we saw more people would answer D. Wrong. Yeah. So I wanted the Taylor polynomial for tan inverse, which is the antiderivative of this. And this is 1 over 1 plus x squared is this Taylor series with x to the 2k, but I want the antiderivative of that to have the Taylor series for tan inverse. There was another question somewhere. Yeah. Where's the constant? So it's, think of it as integrating term by term. So for each term, negative 1 to the k is the constant. Yeah.
How did you get like the last, very last step, like from the series to the x
Here. So I just plugged in k equals 0 to this formula, and then plugged in k equals 1 to that formula. Okay. Other questions? How we doing? All right. Okay. Any other questions on this? Before I go to another example? Yeah.
Isn't that only like the second term? I'm like confused.
Oh, it's the second term, but it is the third degree term. There is no degree 2 term in this one. So.
Okay, thank you.
Yeah. So to get from here to here, just take this, evaluate the sum. So k equals 0, then it's negative 1 to the 0, x to the 1 over 1. So, and so on. Okay. I didn't prepare a slide, but someone asked me about S. Oh. How do I get rid of this? Okay. Someone had asked me about doing these approximation type problems. So here's one. Estimate natural log of 1.06 using a Taylor series with 3 terms and bound absolute error. Okay. So, first thing we want to do is find the Taylor series. Natural log of 1 plus x. We can do using ones that we already know. Because natural log of 1 plus x is the antiderivative of 1 over 1 plus x. So we want to look for the antiderivative of this guy, which we've been playing with already. And there we go. I did all that relatively quickly. Then questions.
How come when you integrate things, it doesn't advance or it doesn't change?
So there's no variable, so it's just like a constant.
Oh,
Yeah, we're integrating with respect to x. Okay, so you guys happy with that? Look out. All right. So we have a Taylor series for this guy, but we only need the first 3 terms. So we can evaluate this. So let's call it step 2. First 3 terms. So natural log of 1 plus x is about, and if k equals 0, then it's x. And if k is 1, then it's minus x squared over 2. And if k is 2, then it's plus x cubed over 3. So there's the Taylor polynomial with a 3rd degree Taylor polynomial for natural log of 1 plus x. And then we use this to estimate. Natural log of 1.06 is the natural log of 1 plus 0.06, which is about 7, 2.
So was what you just did the same thing as taking ln of 1 plus x, taking the derivative 3 times and plugging it in?
Yeah, so how do you say that? Or you get this, you could compute f prime of x, f prime double prime of x over 2, f triple prime of x over 6, and you'll end up with the same coefficient. Yeah.
Do you only get factorials when you do it from derivatives?
The factorials come in when you're doing it from derivatives. Yeah, if you're doing it from another series, the factorials are already built into it. Which I forgot in my mind. Yeah.
Also, like, I just remember when I first started doing it, especially for the homework, like, you would do the Taylor series and you'd forget to do the 1.06 minus like
Yeah.
1. And so you'd end up getting like a way bigger number than you're supposed to. So you have to remember like the x minus a part in the Taylor series.
Yeah, okay, so, right. So the question, I think the issue is that you would plug in 1.06 for x, but the function we're doing, at least that I picked, was math log of 1 plus x, so x is just 0.06 if you're given this function. We could have done Taylor series for log of x, and then you would plug in 1.06, but you'd have to do that around the point x equals 1, because log of x is not defined at 0, and so on and so on. We couldn't use the earlier series to figure it out. If all that makes sense, if any of that makes sense. The idea is you have to pay attention to what exactly your function is, so what x should be. Questions?
That last part without actually error, did you do that? What does that mean?
I'm going to do that right now.
No, if you're doing it tomorrow.
Okay, so this is our estimate. And an error. So this goes back to Taylor's theorem. If Rn of x is the error after x, after n terms, then this is given by n plus first derivative at c divided by n plus 1 factorial x minus a n plus 1. For some c between x and a. Right, so this is the one I said is like generalization of the mean value theorem. So basically the idea is the error is going to be smaller than the next term. And it's not exactly the next term, but it's very close to it. You just have a c instead of an x. So in our case, and we should have done the Taylor series using derivatives. Well, fourth derivative of x, of the function, I must have done it somewhere. Okay, I'm going to count on you guys to be able to compute the derivative 4 times. But it's negative 6 over 1 plus x.
Whenever that you figure that out, knowing the series, if you know the coefficients would have been.
You could figure out the derivative evaluated at 0. You can't figure out the derivative itself just from knowing the coefficients. So you could get close to it, but for your homework problems and so on, you have to get be more exact. Okay. So it's your derivative, your fourth derivative you do with your derivatives is this. And then you find a bound on it. Like this is always less than, we'll take absolute. We'll worry about absolute error, not whether it's positive or negative. That thing's always less than 6. right? So the remainder is given by this for some value of c. We don't know what value of c is, but it has to be between x and a. So it has to be between 0, which is a, and 0.06, which is x in our case. And so we look at this and say, well, if it's 0, the error is 6, and if it's 0.06, then it's well, less than that. So no matter what, it has to be less than 6.
Although if it's 0 and it's 6, isn't 6 equal to 6?
I'll put a less than or equal to. Yes.
How did you decide that it was 6 was the greatest value?
So this function is decreasing. And so its biggest value is going to be at the smallest x value of our range, which is 0. Say it that way. I want to make sure I finish, so I'm going to finish it and then I'll take questions. So the error for x equal to 0.06 is less than 6, which is coming from here, divided by 4 factorial, that's n plus 1, times 0.06 minus 0 to the 4th power. You plug this into your calculator, you get 0.000000324. So after 3 terms of approximation, you are no further off than this. So you know your answer is at least that good. That's the absolute, a bound on the absolute error. Okay, now I'll take questions. Pretty sure someone has, yeah.
So in that like equation, we feel like that n plus 1 of c,
Yeah.
you know, we got -6 over the 1 mentioned before. And like I understand it's less than or equal to 6, that's not part of like we just moved up to -6 instead of the whole thing.
Okay, so yeah, why don't we do this? Why don't we take all of this and plug it in here? We could, but then we would still have a variable in here. So we'd say the error is less than this expression involving x somehow, which is not quite as helpful. Basically, we just want to say, okay, just find the biggest possible thing that error could be, which is why we say, oh, the biggest it could possibly be is 6. Or the biggest this value could possibly be is 6, so the biggest the error could be is this. Other questions? Yeah. My office hours are Mondays and Wednesdays from 12:30 to 1:30. Just show up anytime you need for an appointment. Other questions? Okay, Wednesday is going to be all review. So there's a review sheet up there. Solutions will be up there at some point, but tons of questions on whatever you want.